All right, we're going to go ahead and get started here. This is Max Herzog speaking, Program Manager of the Cleveland Water Alliance. We're really excited to partner with YSI and Xylem on this webinar today on how algae sensors work. And as I'm sure a lot of you are aware, this is actually one webinar in a 5-part series that Cleveland Water Alliance and YSI are going to be doing over the next few months. Each of these sessions is going to be focused on one of these 5 critical water quality parameters that are being collected by lots of different folks using different sensors across the world, really digging deep into how these different parameters can be leveraged to help us understand water quality. And just by way of a little bit of background, Cleveland Water Alliance is a water innovation cluster based in Northeast Ohio, but working Lake Erie region-wide. So we're a nonprofit organization that collaborates with a cross-sector group of partners to really accelerate the implementation and development of new innovative technologies within the water space. And for us, that looks like a couple of different key program areas. First one is innovate. That's really about the development, acceleration, implementation of new technologies, whether that's in academic research context or in private sector context. The next piece is really focused on the connection between different innovators within what we call a broader innovation ecosystem. So Cleveland Water Alliance serves as a hub for the Lake Erie region to connect research institutions with private companies, with utilities, to really de-risk the process of innovation and accelerate the time it takes a technology to move from R&D to implementation or market-based impact. And then finally, it looks like what we call elevate, which is giving us as a Cleveland Water Alliance the capacity to go around nationally and internationally to talk about the Lake Erie region as this hub of water innovation and start to bring the different partners and collaborators like YSI into new spaces and offer them new opportunities by leveraging Cleveland Water Alliance as a platform to elevate the narrative around water innovation, the blue economy, and the significance of those factors and the health of our communities. And this is just to give you a sense of the different kinds of partners we have engaged. Obviously, industry forms really a huge core of that collaboration. A lot of our members are engaged in water innovation from a corporate or private sector perspective. However, we also work really closely with utility partners, academic and federal research partners, as well as a broad variety of government, nonprofit, and foundation supporters that are all interested in engaging in this innovation ecosystem that we facilitate. And with that, it's my great pleasure to introduce Dr. Stephanie Smith. Stephanie is going to be running through the bulk of today's presentation. She has a PhD in microbiology from The Ohio State University, and she's really an expert in blue-green algae and their toxins. She serves as the project segment manager for outdoor water quality for YSI and has over 20 years working with algae and other photosynthetic microbes. We're extremely fortunate in the Lake Erie region and here in the U.S. nationally to have the benefit of Dr. Smith's expertise. And with that, I'd like to hand it over to her to run through today's content.
Great. Thank you very much, Max. We are really, really pleased to be working with the Cleveland Water Alliance, not only on this webinar series, but on a number of projects that we look forward to executing with them. So let's go ahead and move on just to let everybody know, and I can see already that some of you have figured a way around the GoToWebinar panel. Make sure that you can hear us loud and clear. If you can't, type in a question for us. And throughout the presentation, I really encourage you to ask questions. We'll pause here and there for some polls, and while those polls are running, sometimes I'll try to get to some of the questions right away. And then you can also use the chat panel. So my colleague, Nate Christopher, is here with me in Yellow Springs, Ohio, and he's sort of running stuff behind the scenes for us, and he'll be keeping an eye on those chats and questions in case you need his assistance with anything. So with that, this webinar is going to be divided into 4 parts, and we'll hop right into discussing a little bit of why people monitor for algae. So before we do that, I want to run that first poll. This will be good practice for us. Nate, go ahead and tee that up. We'd like to know, for those of you that are attending today, what your primary interests are. What are the reasons that you are interested in algae sensors? And sometimes that feedback that you give me on these polls, it'll be kind of like the old choose your own adventure book. Sometimes I'll emphasize certain things or take us in a different direction depending on your interests. So looks like we have about 60% of the audience that's voted. Let's get a few more in there. Maybe we can get up to 80%. We still have people voting, so we'll keep this poll open just a few seconds longer. I really appreciate the high level of response. Okay, looks like we flattened out at about 89% response. Why don't we go ahead and share the results of that poll? Looks like nearly half of our audience is interested in drinking water source monitoring, and we're really delighted to have you guys here, as we are everybody else. So let's see what we can do to address everybody's interest in this webinar. So let's talk about why people do monitor for algae. One of the first things I always do is remind people of what I'm referring to by algae. Algae, like plants, are photosynthetic organisms. They can be categorized in a number of ways. And sometimes scientists will cringe a little bit at the way I'm doing it here, but bear with me, there's a reason for it. It's convenient for those doing monitoring to separate out the macroalgae, such as the red, brown, and green algae, sometimes we call those seaweeds, from the microalgae or the single-celled algae. Personally, I divide the microalgae then into the blue-green algae, which are actually prokaryotes, meaning they are cells that lack a nucleus. In other words, they're bacteria, not actually algae, but they do photosynthesis like algae. The eukaryotic algae are those things that cause red and brown tides, as an example. What all of these microalgae have in common, though, is that you can find them in the water column in both fresh and marine environments. So people monitor algae for a number of reasons, such as those listed here for the academic research types. And I know that we do have some people here based on that last poll that have a little bit of a scholarly bent. The main reason I personally started studying algae were for some of these reasons. It was years ago when I was studying carbon fixation at Ohio State, and I was very interested in the enzymes involved in that, which of course carbon fixation is a major part of photosynthesis, which is sort of graphically represented here. But today, and I think as our poll exemplified, the main reason we hear about for people to monitor for algae are concerns over drinking water safety. Whether it's my home state of Ohio here, where we had the water shut down in 2014 in Toledo, to the more current situation in Salem, Oregon that occurred last summer, New York to Florida. Florida had one of the worst red tides on record last year. Almost all states in the U.S. are now dealing with harmful algal blooms and have a need for algae monitoring. So each of these people brings a different perspective to algae monitoring. A scientist might be interested in how a lake switches over from what we sometimes call healthy algae like diatoms to unhealthy algae like the blue-greens, and a scientist will probably cringe at me using those terms. A drinking water manager, though, would definitely think of it that way and is concerned about the quality of the product he's delivering. And of course, sometimes the public might be on vacation down there in Florida wondering if it's safe to swim at Sarasota. These are all reasons why we need to monitor for algae. So let's get into that next section of our webinar and talk about the evolution of algae monitoring. And I want to kick this section off with a quick poll also, Nate, if you don't mind teeing this up. I want to learn whether our audience has experience with some of the tools that I'm about to discuss, and your level of experience or curiosity will help drive how I focus on these. Okay, looks like we've got about 80% of people in this audience. So I look forward to explaining a little more about these technologies. Those first three technologies that a lot of you have used are definitely the ones you're going to hear the most about today. So there is definitely an evolution of algae monitoring tools, and by all means, I'm not covering all of the tools. As an example, DNA technologies are kind of coming on strong these days, but I'm trying to walk us through the most commonly used tools and the ones that I think are still probably the most useful. So let's talk about microscopy. Today there are lots of types of microscopes, but it did all begin as far back as 1674 when Van Leeuwenhoek described the blue-green algae Spirogyra, which was actually the Today, microscopes are still popular for algae monitoring because even though it can require considerable skill, it is a relatively low-cost piece of equipment. It is still the most popular tool for enumeration of algae, but I do always warn users that there can be wide variability in the enumeration performed between one analyst to the next. As spectrophotometers and fluorometers became available, pigment analyses became standardized methods for assessing the relative abundance of algae in environmental samples. The unit of measurement used in chlorophyll analyses is a microgram of pigment per liter of sample. Sometimes you'll hear me refer to that as a part per billion or a ppb. Chlorophyll is generally measured today using a fluorometer or an HPLC with a fluorescence detector, though standard spectroscopy is still used. Bear in mind, spectroscopy is really just measuring the absorbance of light that passes through a sample. This persists as one of the most popular monitoring tools. Of course, that is in no small part aided by the fact that the EPA has a standard method, method 445, that everybody loves to use. But as we will see a little bit later in the presentation, sometimes the popularity of chlorophyll analyses can present some challenges for us. Today, we're going to spend the vast majority of our time talking about sensors that are placed directly into the environment for assessing the abundance of algae. The sensors are really detecting algal pigments, not actually algae, and they're used to look at changes in algal abundance. I'll talk a little bit later about the challenges of correlating these measurements with the classical tools like microscopy and chlorophyll extractions. And these tools, I think as our poll also showed, are rapidly becoming the most prominent for direct monitoring in the environment. We won't talk a lot about satellites. Sensors are now being complemented by these hyperspectral analyses, which occur at a gross scale. We won't discuss this a lot today, but I do want to point you to an update that just came out yesterday. I've got the hyperlink provided in this slide, and I want to thank my colleagues that forwarded this on to me. This is about the dead zone in the Gulf of Mexico, and it demonstrates the utility of this satellite technology. So this technology was used to predict that the dead zone this year is going to be the size of the state of Massachusetts, close to the record size that was set in 2017, and exceedingly larger than the 5-year average. So this type of a forecast or prediction is really one of the main points of usefulness about these satellite technologies. Finally, I want to just touch on online analyzers, which to me is the most exciting technology, and it's now becoming a little more mainstream. A good example of this is called the CAM, which is made by a company called Fluid Imaging Technologies out of Maine. These may combine the best of all the methods I just mentioned, even supplying images and analyses of species, quantifying microbes in a sample. It's still a bit expensive, so it's a little pricey, but it's not ideal yet for real-time continuous monitoring the way in situ sensors are used. But I think it's a matter of time, frankly, before this becomes one of the most prevalent algae monitoring tools, because you really get a lot of bang for your buck out of this technology. So to summarize this section, I want to leave you with a number of points about these tools. First, just because a tool is old, like microscopy, doesn't mean it's not useful. And don't think that the best programs really mix it up using a number of technologies, including some tools that I didn't discuss here, such as DNA analyses. If you guys aren't familiar with it, at YSI.com, you can download a copy of a magazine that we publish called Mission Water. And I do a nice overview of these same technologies in an article I wrote in issue number 6 that just came this month. So now let's move into the real meat and potatoes of our webinar. This will be our longest section, and it's where we're going to really get down to the nitty-gritty of the principles underlying these algae sensor technologies. I want to start by doing another poll. Again, this might help me know what to emphasize in the presentation. Why don't we tee up the next poll, if you don't mind, Nate? Asking people what types of algae they're most interested in monitoring for. This will help me to understand what sensors you might be most likely to use. So we're getting really good response on this. Let's again try to get that response rate up to about at least 80%. Okay, really good turnout on this poll. Looks like about 85% voted, and 86% actually. So not surprisingly, it does look like most of our audience is interested in freshwater blue-green algae. But I think you're going to find, no matter who you are, that a lot of what I'm going to discuss is going to be applicable to most of these types. Now, one thing I will mention, those of you who are most interested in the macroalgae, the sensors that I'm going to discuss today really do have limited applicability to those macroalgae. So maybe after I explain this, how these sensors work, it will be apparent to you why that is. So we're going to talk about the principles of fluorescence, which will help us to understand the pigments of algae, which are fluorescent molecules. And fluorescence is really the basis for how not only YSI's algae sensors, but pretty much all algae sensors work in one manner or another. So in case you don't remember this from school, I didn't until a few years ago when I started relearning it, a fluorescent molecule is one that can absorb light, termed excitation, and which also emits light, termed emission. The electromagnetic spectrum is shown here to remind you that the shorter wavelengths of light on the blue end of the visible spectrum have more energy than longer wavelengths of light as you move towards the red end of the spectrum. When a fluorescent molecule absorbs light energy, we say that it is excited, and eventually it must return to its original energy state. There are three fates for that energy that it absorbed. Some of it is lost as heat, some might be passed on to another fluorescent molecule, as we will see in a moment, and some is released as light of a longer wavelength, which is, again, of a lower energy. Chlorophyll, that we all know and love in the algae world, is one such molecule. It absorbs high energy blue light, becomes excited, and then as it comes back down, it's going to emit red-orange light. The fate of the energy it absorbed is unique. Some, of course, is lost as heat, some is emitted as light, as shown here, but what's unique is that some of that energy ends up in the chemical bonds of sugar during the process of photosynthesis that again is represented here. That sugar fuels the growth of all photosynthetic organisms, including algae. In other words, this is the way that energy and carbon get assimilated into the biomass of the algae. But it ends up that chlorophyll doesn't always work alone. Now, this is a really relevant point for those of you that are looking at types of algae that are not freshwater blue-green algae, chlorophyll is found in all aquatic algae, all of which use it for photosynthesis. So any of the sensors we're going to talk about today can detect chlorophyll and would be relevant for monitoring of any type of microalgae. Blue-green algae also have a complex of pigments called allophycocyanin and phycocyanin. Sometimes you'll see this just called PC in this presentation. Freshwater blue-green algae have very high concentrations of phycocyanin, which is responsible for the bluish hue some of you are familiar with if you've seen them on the surface of Lake Erie, for example. Blue-green algae in marine environments additionally have a pigment called phycoerythrin. These pigments act in concert as what is called the phycobilizome. Sometimes you'll see this in the literature referred to as the light harvesting antennae of blue-green algae. The pigments are integral to the high rates of photosynthesis that blue-green algae can achieve, so that when they have all other critical nutrients, such as phosphorus and nitrogen that we hear so much about, they can grow in a way that outpaces other types of algae in a system. These pigments do all the things we said fluorescent molecules can do. They can selectively absorb specific wavelengths of light from the sun. They will lose some of that as heat. Some of that energy will be lost as a specific wavelength of light that they emit. And some of the light energy they release actually is going to be absorbed by chlorophyll, which is in contact with that phycobilizome structure. So in this way, these accessory pigments, as we sometimes refer to PE and PC, in this way they channel the energy they captured to chlorophyll to drive photosynthesis. A sensor is going to take advantage of that natural process. Instead of sunlight, the sensors I talk about today use an LED that emits specific wavelengths of light to excite one of these pigments. And specific wavelengths of light emitted by that molecule are either going to be absorbed by another pigment or are going to directly go to a detector, as shown here for chlorophyll. Folks, I hope you're still with me. I apologize. It looks like we are having a few sound issues, but we're going to keep working through it. Stick with me. So I'm going to back up here and talk again about fluorometers. So fluorometers have been used for decades in the laboratory. Every fluorometer has a light source, typically some type of a lamp that emits a wide range of light wavelengths. The fluorometer is going to have an excitation filter, shown here on the left, that narrows the range of wavelengths to include those that can excite the molecules of interest in your sample. That filtering is not perfect. Other molecules in the sample might also get excited by light that passes through the filter. Thus, there is an emission filter on the other side, which narrows down all the light emissions from the sample to those that are specific for the molecule you're trying to detect. This filtering gives you great specificity, meaning that you will mainly, or ideally only, detect the molecules you are trying to measure. Now, through the years, fluorometers have also afforded great sensitivity, meaning you can detect lower levels of the molecule in the sample than ever before possible. This is one of the reasons that fluorescence is such a popular tool. So the challenge, though, is how do you bring that fluorometer principle, which happens in something about the size of a square foot box, down to something about the size of a small cigar, such as you find in the sensors of YSI's EXO and ProDSS platforms. That's one way that YSI advanced this technology. It's in the packaging. So we're going to talk more about that packaging and the engineering principles for how these sensors work. Going forward, as an example, I'm pretty much going to focus on these EXO sensors that you see on the top. So in the interest of time, we're going to skip over the importance of the wetmate connector, the titanium housing, and the sapphire lens that are all unique features of YSI sensors and are part of the reason that our sensors are so rugged in the field. Instead, we're going to focus on how we leverage principles of fluorescence and fluorometry where specific LEDs and filters will allow us to excite the molecules we care about, and a photodetector, which you may also hear me call a photodiode, will see the light emitted by chlorophyll. You may recognize these as the same basic components of a fluorometer. Now, in the case of YSI sensors, we call these dual channel sensors. This is unique because each sensor can excite two pigments. Every sensor can excite chlorophyll, but then you can choose either a phycocyanin exciting sensor, which we call the total algae PC sensor, or a phycoerythrin exciting sensor, which has a green LED, and we call that the total algae PE sensor. Most people that do freshwater monitoring, which judging by our poll seems to be most people on the webinar today, are going to use the total algae PC sensor, and we're going to discuss that one first. Again, the two channels on this sensor are a chlorophyll channel with a blue LED and a phycocyanin channel with an orange LED. The chlorophyll pigment in the water is excited by the blue filtered light put out by the sensor. That excitation band is 470 nanometers plus or minus 15 nanometers as shown in the table here. If you were to look at the older or competing technologies, you're going to see that the excitation wavelengths used to have a much wider bandwidth around them. Thus, this is really reflecting an improvement that better filtering technologies have brought us to today. The photodiode detects emissions from chlorophyll at a peak wavelength of 685 nanometers, again with a very tight bandwidth filter of 20 nanometers. The phycocyanin channel is likewise excited by a tight wavelength band, this time in the orange region of the electromagnetic spectrum. But here is where we do something rather unique. The light emitted by the phycocyanin reaches the detector, but due to the filtering on the photodiode, most of it is filtered out. Instead, leveraging the natural process of transfer of that energy to chlorophyll, the excitation of phycocyanin will ultimately lead to the excitation of chlorophyll, and the light detected by the photodiode is from chlorophyll. This is very unique to YSI sensors and is among the reasons that our sensors are really, really sensitive. We use the phycobilizome as a signal amplifier and only detect chlorophyll. The same principle happens with the total algae phycoerythrin sensor, which has a green LED. The chlorophyll channel works exactly as we just discussed, but the phycoerythrin pigment is excited by a green light at about 525 nanometers. The transfer of energy to chlorophyll and the emission of light from chlorophyll is what the photodiode sees. So you may be wondering by now how the sensor, if it only detects chlorophyll effectively, is really telling the difference between these pigments. We'll get to that in a moment, but for now, let's talk about the brains of a sensor, its printed circuit board. Every sensor has a PCB. Now, honestly, I'm a microbiologist, and when I started working at YSI 3 years ago, I did just have my 3-year anniversary, I came to learn that the circuitry in the sensor is sort of like a car engine in idle. It's always humming in the background and causing a baseline signal that we actually call the noise. So if a board is designed using older methods, or frankly, if it's just not very well designed, fortunately for me, we have some of the best board designers here at YSI, that car engine is idling higher and the noise is higher. This makes it a lot harder for the sensor to know what the real signal is that is coming through the board via the photodiode. That photodiode is connected to that circuit board. Good board design then leads to good signal to noise ratio. Sometimes we call that SNR, which leads to lower detection limits. This is one of the principles that separates good sensors like our 6 series sensors from excellent sensors like the EXO and ProDSS sensors. Great sensitivity without sacrificing the specificity for the pigments you want to detect. Now, our software engineers come into play. So specificity is further optimized through firmware, which I also learned at YSI is a fancy word for the software that resides within the sensor itself. Modulation of optical frequencies means that the sensor has software which enables it to reject noise and out-of-band frequencies so that sensors don't interfere with one another. I think of this as the tools used today in the pop music industry, actually. So Katy Perry's recorded voice is not native. It is modulated to have perfect pitch and tone when you listen to one of her recordings. If you heard her in person, she would sound quite a bit differently. The firmware also aids in what I will refer to as electrical filtering. Stray light does reach the photodetector. How does the photodetector know what light came from the stuff you care about? It knows via timing, in a manner of speaking. This is the answer to the question I posed on the last slide about how the sensor knows when the signal comes from chlorophyll excitation or excitation of one of the other pigments, phycocyanin or phycoerythrin. The LEDs that excite these pigments are not all firing all the time, or even at the same time. They are pulsed at specific frequencies, and the firmware allows the sensor to tease out the relationship between the timing of the LED pulses, and the firmware allows the sensor to tease out the relationship between the timing of the LED pulses and the timing of the signals that reach the photodetector. So finally, every individual sensor is tuned in our factory. When sensors became so sensitive as they are today, it became almost impossible to make them identical during manufacturing. Bear in mind that at YSI, every sensor is put together by hand by some extraordinary people that are actually in the building that I'm sitting in right now. One thing we must manually normalize is how power flows through the LED from one sensor versus another sensor. This is a principle I'm going to touch on in the next section again when we talk about calibration. So getting close to wrapping up this section, I talked about several of the hardware features as well as firmware features, and I've tried to summarize that up in this table. And the message here is that form drives function. The quality of the components, the quality of the engineering, all have an impact on the quality of the sensor. And bringing all of those things together in one package is, frankly, something we've been doing very well here at YSI for many years. A good example of how the technology has evolved and improved can be seen by comparing the 6 series phycocyanin sensor to the phycocyanin channel of the EXO sensor. Remember me talking about those bandwidths being tighter, and you can definitely see that on the excitation and emission optics shown here in the table. That means on the EXO you get much better specificity when you excite that phycocyanin molecule. The other nice thing is you don't need as much power to excite the molecule. The EXO sensor is a lot less prone to interferences and non-specific signals, and then that firmware gives us an extra boost that gives us a 10-fold better sensitivity. So form does drive function. Firmware matters as much as hardware. And the best sensors, of course, which I think some of which we have here at YSI, are going to balance all of those things to give you great signal-to-noise ratios. So I'm going to pause here. That was a very, very dense section. So before we go on to talk about practices, we have some really good questions here that I think I want to pause and take a look at. So one of the things Elizabeth has asked is, how long do cyanobacterial pigments persist after the organisms die? I hate giving you this answer, Elizabeth, because the answer is, of course, it depends. So when a cyanobacterial cell dies, for example, some of those pigments are just released directly into the water, and those pigments will expire pretty quickly. Some of them stay attached to the dead membranes, and they are going to last as long as some of those membrane processes still can deliver energy to those pigments. So, but frankly, after the cells die, the pigments go away pretty darn fast. I don't have an exact number for you because it really does depend on the organism, the quantity of the pigments, and the conditions of the water. So for example, if it's very acidic or very alkaline water, the pigments can die faster. Those things will have an impact. And this is a great question, one that has plagued our industry for years, and I remember asking it back in the lab 20 years ago, which is whether you can distinguish live from dead bacteria, which of course relates to Elizabeth's last question. These sensors do not allow you to make that distinction. If you want to distinguish live from dead bacteria or cyanobacteria, you really have to use different tools to do that. There are different types of fluorescent stains that can be used in the laboratory to do that, but these sensors really are not designed to help you make that distinction. So that's a very important point that Elizabeth has helped us to make. Martin asked me to comment more on interference. So for example, he said that he's getting higher chlorophyll and phycocyanin readings near the bottom of his reservoir when turbidity is higher. So this is something that we have heard before, and it's definitely something that older sensors and what we call single channel sensors are much more prone to than the exo sensors. So the bottom line is this: as you guys have seen, light passes out of the sensor into the water, and then it has to come, something has to come back into the detector. If there's a lot of stuff in the water, it's going to interfere with how that light acts. And some of that stuff can give you an artificial fluorescent signal. Some of that stuff can just reflect light back into the sensor, giving you an artificially positive signal. So, and the other thing that can happen is you can get more typical, Martin, what you would see with high turbidity is a lower signal because light can't get back to the detector. So it really depends on what the nature of that turbidity is. If that turbidity has a lot of fluorescent material, it might give you an artificially positive signature. If that turbidity is a lot of sediment that blocks light passing through it and getting back to the detector, you get an artificially low signal. And definitely, again, old sensors and some of our competitor sensors that are only single channel sensors are far more prone to that. So let's see, we've got quite a lot of great questions, you guys. I really appreciate this. One of the questions from Alexander asks about how similar is the pulsing of the total algae sensor LED to the pulsed amplitude fluorometry, or are they the same? I have to be honest, I'm not exactly sure on the answer to that question, Alexander, and I see that maybe Amy has asked a similar question. So what I'm going to do is set that one aside. It's a really excellent question, and I'm going to get back to you on it. So we're going to go back and research that because off the top of my head, I'm not sure about the answer to that question. Saul has asked a question about how best to calibrate the sensors to be able to compare readings between the 6 series or EXO sensors, 1 point, 2 point, using pigment. Saul, that is a great question, and what I'm going to do is come back to that question in a moment because we're going to talk about calibration as the first part of the next section of the presentation. So let's go ahead and start that part of the presentation about the best practices that one can use when working with algae sensors. So I have a little bit of a pop quiz question for you here that I'm going to ask Nate to kick off. And the question is, what do you think is the biggest challenge people face when they are monitoring for algae? I've given you 3 options here. You may have other ideas as well. Okay, Nate, I think we've probably got about as much response as we need to see what most of our audience believes is the answer to this question. I'm really excited to see your responses to this because I think you might be surprised about what I'm going to tell you I believe the biggest challenge is when people are monitoring for algae. So let's hop to that. Now, one of the things, and some of you that are on here probably already know this, I've done a lot of algae webinars. It's kind of become a joke around here that if you're not sure what Stephanie is doing, she's probably preparing an algae webinar. I love doing this, and one of the things I've discussed in a number of those webinars is how to look at and interpret data. So we all love to talk about the finer details of algae monitoring. Some people want to ask whether different types of chlorophyll, by the way, there are 6 types, whether those different types are, which pigment channels should give what outputs during an algae bloom, and so on. What works best in saltwater versus freshwater? So I touch on some of these questions in a blog I wrote earlier in the year if you want to see the things that I most frequently get at. But the funny thing is that in practice, a lot of these really detailed questions are rarely the types of things that trip users up. The most fundamental things like calibration, fouling, and really understanding what the units of measurement are telling you are what prevent people from getting the most out of their algae monitoring. So in this last section, we're going to touch on these 3 things. So I mentioned earlier that sensors are hand-built here at YSI, and one consequence of that is that the raw voltage output of a signal, in other words, what is seen on that PCB, that is what is modulated by the firmware that I talked about, and that cannot be the same for every individual sensor. That's simply a function of physics. So in the factory, the first thing we do is tune the sensor so that a 0 to 100% relative fluorescent unit scale is completely linear for every sensor that we sell. Again, though, that RFU scale is not necessarily identical between individual sensors at the point of manufacture. And further, as you use a sensor, the output of the sensor may slightly drift so that the sensors are no longer identical in their outputs. So there are a number of reasons that sensors drift, including the age of the LEDs, which by age, I don't mean the age since when you purchased it, I mean how many hours of use the LED has on it. How long since you purchased it, the environmental conditions, the quality of the engineering, power surges, all of these things can cause a sensor to drift. And by the way, beware of vendors who tell you that they have drift-free sensors. Well-engineered sensors can indeed drift so slowly as for drift to be undetectable. We have many YSI users who really only calibrate their sensors at the beginning of the algae season. But be aware that optical sensors in particular of all types will drift. So these are the reasons that we calibrate sensors, and also why it is prudent to periodically check sensors and when necessary, calibrate them, recalibrate them. So how frequently you have to do this is one of the most common questions we get asked, and it depends upon all of those factors I mentioned in the last slide, like the age of the sensor, the environment, and so forth. But most importantly, calibration aligns the output of sensors so that the data collected with one sensor can be compared with the data collected by another sensor, such as when you replace a sensor on a sonde, or if you're monitoring at multiple sites and want to compare the data from those sites. So I want to address some language, and Saul, this might at least partially address your question that you gave us in the last section that we use in the industry regarding calibration. Very often you will hear people refer to a one-point calibration. Now, I grew up in the lab world. I'm a lab rat by training, and in my mind, 1 point is not actually a calibration, though in some cases it's appropriate to do that. So in the case of these algae sensors, using a water standard to basically reset the 0 point on the sensor is a 1-point calibration. So if you are using 3 different sensors in your study, those sensors will read very closely on the lower end of their RFU ranges if you've done 1-point calibrations. Now, depending upon how differently they were reading at the higher end of their ranges at the outset, they could end up being quite different at the higher RFUs. So if you are mainly doing detection of low concentrations of algal pigments, a 1-point calibration might be just fine for you. If you are working in an environment where readings will be higher, my personal cutoff point is 15 to 20 RFUs, I strongly recommend a 2-point calibration. A 2-point calibration will use a second standard somewhere further out in the RFU range, and it basically snaps all those sensors into line so that you can compare the reading across the entire RFU scale for those sensors. People doing harmful algal bloom monitoring who have a reasonable expectation of a bloom event should do a 2-point calibration. That is your best practice. Now, it may seem obvious when you're working with an optical sensor, clean. So keeping the face of those sensors clean, the calibration tools clean, that is really important at the point of calibration of any optical sensor, not just the algae sensors. If you are using the EXO platform, you really should take advantage of that multi-cal feature. And again, though, with optical sensors, cleanliness really is next to godliness. In some of our future webinars, when we talk, for example, about turbidity, this will be a really important topic, and Carrie Hubbard may talk to you about that. So if you haven't already, you might register for that webinar to learn more about that. But biofouling, this is my answer to that poll question. So a lot of you felt that improper calibration of the sensors is the biggest issue in algae monitoring. I actually tend to disagree, and here's the reason. Calibration is helping you to align those RFU scales. But really, when it comes to in situ algae monitoring, what you're doing is you're monitoring for a baseline activity in the water, and in an algae bloom, you're looking for a big change from that baseline. The actual final value, whether it's in parts per billion of pigment or cells per liter or whatever, almost doesn't matter. It's the change relative to a baseline. So in my opinion, calibration certainly matters, and we all want the most accurate measurements, but boy, biofouling is really what seems to trip people up. It's one of the most fundamental issues of continuous monitoring. It costs people lots of time and money. So we're going to quickly review why it matters and a handful of things you can do about it. So I'm showing you here data that is 10 years old, but the principle it demonstrates still holds. So the top panel shows the chlorophyll A readings from one of our old 6 series sondes, which had a mechanical wiper on the individual sensor. Okay, so the yellow dots are chlorophyll A extractions of samples collected at the same site, which is something we're going to talk about again in a few minutes. On the bottom is a competing high accuracy chlorophyll sensor that shall remain unnamed, but which is still sold in the market today. This sensor has been pegged, and by that I mean that the sensor thinks there is an amount of chlorophyll that is maxing the sensor range out. That's because light is not penetrating the biofilm on the sensor's face. There's actually a mild growth of algae on the face of the sensor, and all the signal from that biofilm is directly being bounced right back to the photodetector. So this is a misleading outcome, and I see this all the time. Biofouling really will mess up your sensor, and if that biofouling is algae rich, you're going to think you have a lot more algae in the water than you actually have. The EXO platform has a central wiper, so that 6 series data I just showed you, the individual sensor was wiped. In the EXO, we have a central wiper that keeps all of the sensors clean. Yes, I do believe it's the best in the industry, and the efficacy of it is shown here. We're also showing the usefulness of copper. Copper is toxic to most aquatic organisms, and we have a copper sonde guard that slips over those sensors and which was used in this deployment. As you can see in the middle picture, this was a very high fouling marine environment, but the sonde guard doesn't have hardly any growth on it. The wiper, if you look on the right-hand side, kept the sensor faces clean. So this really demonstrates a very dramatic effect of two of our best tools to fight fouling, that copper sonde guard and then that central wiper. It ends up, there's even copper tape that you can put around the sensors. We have sprays, and even duct tape can be a useful tool in the field. We have a lot of users that cover the body of the sonde with duct tape, and that's really handy, particularly in marine environments, because instead of trying to chip all those barnacles off, you can just kind of break into that tape and cut it off. So, last but not least, I want to talk about one other thing that I consider the best practice to use when monitoring for algae. Listed here are units that are options on a number of sensor technologies, including ours at YSI. And to be honest, hindsight being what it is, I wish our industry had never tried to translate these lab-based measurements to field-deployed monitoring tools. First of all, raw units, those are something that you as a user will never use, but often we use it in tech support and the repair center for diagnostic purposes. We're going to come back to RFUs, but let's reflect for a bit on pigment concentrations, cell counts, and the old school unit called biovolume. Part of the reason that these units are still employed for in situ sensor technologies is that, as I mentioned earlier, as new technologies emerged, we scientists are always most comfortable when we can tie those measurements back to measurements that we are most familiar with and which have become standards, like the EPA method for measuring chlorophyll. So cells per mil, that's often done by microscopy, and pigment concentrations in micrograms per liter or parts per billion are examples of measurements that have been around forever and which most customers want delivered from their sensor technologies. Fortunately, this seems to be relaxing a bit with some of the newer technologies. You don't see this, for example, in the satellite technologies. No one expects you to report cell per mil with that. But this does present a real challenge for sensor technologies. So in the field, refreshing your memory here, some of you have done this, I'm sure. You collect a sample, you filter it to grab the algae onto that filter, and then the filter is extracted with acetone. And that extract is measured on a fluorometer or an HPLC. Sometimes people even still use spectroscopy. Now, that is all great, but here's the challenge. The sonde can also deliver that same unit, and when the part per billion unit, for example, was developed for our sensors as well as other people's sensors, it was done with a laboratory grown culture that is diluted in laboratory medium. We measure the RFU, and then we perform an extraction to see what the yield is in parts per billion. We build a correlation between those RFUs and parts per billion so that when you're doing measurements in the field, the sensor is really seeing RFUs, but it's spitting out parts per billion for you. But really, this is not representative. That correlation isn't built on a process that's representative of how algae act in the environment. In some cases, it's really great. Actually, to be honest, I'm surprised at how well it works for about 60% of people. But in other cases, it isn't so great. And I get asked so many times why people collect samples and they do a pigment extraction and they get a different answer than they get from the sondes. The answer is you need to verify whether extractions, parts per billion, or whether cells per mil are going to be good units for you. And that's exactly what my friend James Chen, working in China, did for a lake he was working on. He collected his own lake samples, diluted them, measured them with the sonde, and went through these same steps we've been talking about. And in his case, the results were spot on. The chlorophyll delivered by the sonde, shown here on the x-axis, lined up beautifully with what he extracted from his field samples. But I just want you to know this is not always the case. And if you want the sonde to tell you parts per billion for any pigment, I recommend that you verify that output before you rely on it completely. I described some of the reasons for the variability in this in the webinar I did last year. I'm not going to go into all of it here. I recommend that you review some of these environmental factors as well as physiological factors that the algae themselves can impose upon the system when you're doing these measurements. We're running out of time, but I'm going to sum up this last point by saying, please use RFUs. People doing monitoring should be looking for changes from a baseline fluorescence. They shouldn't be looking for the sensor to replace their laboratory analyses, and they should be wary about comparability to those analyses. Use the monitoring data to help you decide if or when you want to collect samples. So wrapping up this final section, you need to check your calibration frequently, and whenever possible, do a 2-point calibration, take measures to prevent biofouling, and please use RFUs. And I am going to pause for a moment. We're going to put the last poll up in case any of you want someone from YSI to contact you. Nate has delivered a whole slew of questions to me here, so I'm going to start picking some of those off while we're running this poll. So one of the questions I have here is from Jill. Jill is asking, can I correlate my 600 OMS phycocyanin sensor to my newer EXO phycocyanin sensor? My client is more familiar with the older values, whereas EXO has very low values. So the answer is, Jill, there are a couple of ways you can do that. First of all, if you aren't already, Jill, you should be using the latest version of the Core EXO software, Core 2.0. In Core 2.0, you will find a new module that allows you to actually build your own correlation. It allows you to choose an algorithm that will make your EXO data look more like your 6 series data. Now, to be honest, speaking as a scientist, I feel like this is kind of some shenanigans that we have to do to make ourselves more comfortable with the data. The reality is that the data coming off the EXO are much more consistent and, in my mind, reliable. But you can choose that option. You can also build your own correlation. So you can go through an exercise similar to the one I just described for chlorophyll extractions, but instead of comparing EXO data to extracted chlorophyll, you compare it to data you measure with the 6 series. Build your own core if they're concerned about the transition from 6 series to EXO. Let me see here. Here's a great question from Mohammed. He asks, does the type of water, freshwater, salinity, etc., affect the method of monitoring or parameters and the growth of the algae? So it does, and here's what I mean by that. Now these sensors, so for example, if you take the total algae phycocyanin sensor, a lot of times you'll hear it referred to as the freshwater sensor. The reason for that, because you can't use it in salt water. It works perfectly well in salt water. The only reason we say that is because the algae that you're typically measuring phycocyanin for are in freshwater, whereas marine algae have a more prevalent phycoerythrin sensor. So the real impact is about what the population of algae are that you're looking for. I do have people that use that freshwater phycocyanin sensor in a marine environment, for example, because what they're really looking for is incursion of freshwater algae via rivers or something like that into that environment. But as far as just pure functionality and the optics, now that you understand better how those optics work, those optics pretty much work about the same in high saline environments versus low saline environments. Now, the one exception is deep ocean applications. Occasionally you see some minor differences there, but if you are monitoring for a change in a baseline, you're going to be just fine monitoring in any of those environments with these sensors. So let's see, what does it mean? Oh, so Albert is asking, what does it mean if I have more phycocyanin than chlorophyll? So Albert, your question sounds very simple, but there's actually some very important layers to it, and I really appreciate that you've asked it. So we get asked all the time, by we I mean me, you know, if it's a blue-green algae bloom, should I have more phycocyanin than chlorophyll? Phycocyanin is definitely the better tool for distinguishing growth of blue-green algae from growth of all other types of algae. But sometimes it really depends on the physiological state of the algae as to what those ratios of phycocyanin to chlorophyll are during their growth cycle. So there isn't a hard rule of thumb as to whether you should always have more phycocyanin than chlorophyll. I have done some monitoring situations of microcystis, in fact, where the chlorophyll changed more than the phycocyanin. I'll be honest with you, I don't know why that was. And the thing you have to remember is that pigment concentrations, the concentrations of individual pigments within algae, are not static. They're always changing. They're changing in response to the amount of sunlight present. They're changing in response to temperature. They're changing in response to all sorts of physical conditions. So if you're monitoring and you have more phycocyanin than chlorophyll, you definitely have blue-green algae, but it doesn't mean you don't have other types of algae. So Aaron asks a really important question here, and this goes back to our conversation about calibration. He says, what causes negative concentrations or RFUs? So in other words, what's happening is Aaron is taking, hopefully a calibrated sensor, Aaron, and he's sticking it in water and it's actually reading a negative number. So remember me preaching about everything being, so the reason I went on about everything being so clean during calibration is that is the number one reason this happens, is if that sensor was in water and that water had stuff in it, the sensor has the 0 point set at something that is not actually 0. And then when you take that sensor and place it into water that might actually be 0, it's going to read negative. Now, this is something that all sensors do, not just YSI sensors. And sometimes people, YSI actually had a choice to just make all negatives 0. But we chose not to do that so that users would get a clue just in case their calibration was not perfect. So that's why we enable the software to deliver that negative number. And when you see that, you may not be able to calibrate it out. It's going to depend on a lot of things. For example, not all distilled water is 0. We've had people calibrate with distilled water and then they take it out to the field into an ocean environment where they do have 0 and they get a negative reading. So it's nothing to be particularly concerned about, Aaron. And if you are monitoring, again, if you're monitoring for a change from the baseline, those values way down there are not going to be what's important. What's going to be important to you is when you start seeing those RFUs becoming very positive very fast. So, Henry, great question here from Henry. One of my favorite topics is toxins, and he says, do blue-green blooms always mean toxins are produced? The answer to that is no. If you have a lot of phycocyanin signal, it means you have the potential for having algae that are capable of producing toxins. And just because they're capable of it doesn't mean they're actually doing it. I can't tell you how many times I've collected algae samples rich with Microcystis aeruginosa without a shred of toxin in them. So no, just because you have a blue-green algae bloom doesn't mean the bloom is toxic. Now, with that said, we find in some systems there's a very Lake Erie is definitely one of those systems. So we know that when you monitor phycocyanin on Lake Erie, there is a very good correlation with the presence of toxins. And there have been a number of nice papers that have come out of Ohio State Stone Laboratory as well as the main campus in Columbus on that topic. Oh, here's a really great question from Martin. I don't know if this is the same Martin that asked a great question a few minutes ago. It is. Nate tells me it is. Way to go, Martin. And also, I just want to mention, it is 2:13. You guys are hanging in here. We've still got a lot of people online, and I'm willing to hang out a little bit longer if you're willing to hang out a little bit longer. So I'll probably go here for another 10 or 15 minutes because these are really wonderful questions, and part of the great value of these webinars is getting to interact with you directly. So I'm going to keep going here. So Martin is asking, he apparently had some samples where he was measuring Cylindrospermopsis, and he could see that Cylindrospermopsis was the dominant algal population. He had over 500,000 cells per mil. That's a lot of Cylindro. But both the chlorophyll and phycocyanin signals were quite low, and he wonders why that is. Now, Martin, obviously I'm going to speculate here, but I will tell you I've seen this before, and I've seen it with Cylindro, and there are a number of reasons that I think it is. So first of all, if you ever have looked at a Cylindrospermopsis bloom, you will notice that it doesn't get that intense blue-green color, certainly not at 500,000 cells per mil. It doesn't seem to get that intense color that, say, an Anabina or a Microcystis bloom gets. Cylindro appears to me to not produce as high a density of toxins per unit cell. Now, I don't know why that is. The other thing that makes Cylindro very interesting is Anabina, which is a filamentous blue-green. It forms these, it's not really a filamentous, but it forms these chains. So you get a tight clustering of cells together. Microcystis also forms these microcolonies. And in those kinds of clusterings of cells, you get really high pigment concentrations in sort of a denser area. Cylindro is planktonic. It stays very evenly dispersed in the water column. And for that reason, I think you don't get as high a density of pigment. So when people are monitoring for Cylindro, I talked about monitoring for a baseline. People who deal with Cylindro blooms are usually looking for much more minor fluctuations from those baselines than people who are monitoring, for example, for Microcystis. Again, that's just based on my personal experience of watching this over many years. I know, for example, a lot of our folks in Indiana deal a lot with Cylindro blooms. Oh, Rainey has a great question here. It's an important question. And she says, is there an ideal depth for sensor placement? This is an important question, and it relates to another question. What is the potential impact of ambient light? So there isn't really an ideal depth, but what is important is sort of the orientation of the sonde. So first of all, if you're in a river, for example, you don't want the sonde, the sensor end, the business end, pointed upstream where the water is rushing into the sensor face. You want it kind of in the path of flow of the water, and you want the sensors completely submersed. Ideally, I would say at least 6 inches. But as far as there being an ideal depth, it really depends on what you're looking for. So some of our water managers here, for example, the ideal depth for them might be wherever their intake is. That could be 3 feet under the water, that could be 30 feet under the water. So the ideal depth really depends on your application, but definitely you want to consult the EXO manual, because it really does talk about the best practices for how to put the sonde in the water. And that's where you'll find things like the placement that I was just talking about. Here's an important question from Samantha, and this is something that I'm seeing becoming increasingly important as we get more polluted waterways. Samantha asks, what are the impacts of CDOM? Great question, Samantha, and I appreciate it, because lately it's something that I'm starting to think is more impactful than I used to think. So CDOM, for those of you who aren't familiar, is colored dissolved organic matter. And there is a fraction of CDOM called fluorescent dissolved organic matter. We actually have a sensor for that. It's called the FDOM sensor. I have come to see data in the last year and a half where waters with a lot of color, a lot of CDOM, will interfere at a low level with these optical sensors. So it's going to depend on what composes that CDOM material, Samantha. And this is something that if you are working with highly colored water, I think you should take a look at this. You might find a correlation. So if you take grab samples and you measure them with the sonde, and then you go do your CDOM measurements, or measure them with the CDOM sensor on the 6 series or with the FDOM sensor on the EXO, I would pay very close attention to the correlation, if there is any, between those measurements. There are FDOM rich environments that don't seem to tweak the algae sensors at all. There are other FDOM rich environments that do seem to tweak it, and when I say tweak it, I'm talking like 1 to 5 RFUs at most. But definitely in that like 1 to 2 RFU range, I have seen potential environmental interference that I believe is due to CDOM. This is something I want to do more research on. And Samantha, if you are working in a CDOM rich environment and this is something you can measure for us, I'd like to hear from you again. So Angel has asked whether or not I suggest pulling the sensors during weather where there is little to no algae present, so such as in cold weather. Actually, Angel, I don't recommend that, particularly if you're in my home state of Ohio or somewhere here in the Midwestern US. And here is why. We now get algae blooms that occur under the ice. So for example, there's an organism called Planktothrix rubescens, which blooms under ice. The Ohio EPA has documented that before in the state of Ohio. So quite honestly, I guess it depends on what your monitoring objectives are, but I would say if your monitoring objectives are more academic in nature, this is something I would really want to study some more and learn some more about. So even though in the temperate zones like we live in, we tend to think that algae blooms occur in the warmer weather, and certainly they're more prevalent in warmer weather, it doesn't mean they don't occur when it's cold. And we're starting to see a lot of cold adapted algae becoming more common in our environment. I don't know if it's always been that way, and maybe we just weren't looking. I suspect that might be the case, but I think climate change might also be playing a role there. Oh God, Kurt has asked one of my favorite questions. He's not going to like the answer though. Sorry, Kurt, but here it is. Kurt has asked, how would you recommend doing phycocyanin measurements to corroborate the phycocyanin RFU values? Would you do an extraction or direct aqueous readings? Kurt, this is a wonderful question, and I suspect you may be something of a biochemist or you wouldn't be asking it, but I will tell you, I have worked with phycocyanin a lot, and it is a pain in the neck. So phycocyanin, once you extract it from cells, it falls apart when you look at it cross-eyed. When you extract phycocyanin, you have a number of minutes to an hour to really get a decent measurement off of that phycocyanin. So ex situ, as we call it, or out of the cell, ex vivo phycocyanin becomes very unstable unless it is at brutally high concentrations. So what I would recommend, phycocyanin gets released when you do what are called freeze-thaw cycles. So you can actually collect an algae sample, take it through freeze-thaw cycles, and then measure the phycocyanin directly in that aqueous part after you've removed the dead cells. That sometimes can be useful to you. There is also some commercial phycocyanin on the market. I'd be a little careful when you buy a phycocyanin powder. Typically, it's just powdered spirulina cells. It's not actually pure phycocyanin. The reason for that is that phycocyanin is very hard to purify and keep stable. There is one vendor that makes a pure preparation of phycocyanin. In case you're wondering, this is also why nobody really has good phycocyanin calibration standards. But that preparation will cost you about $1,200 for a milliliter because it is super concentrated. That's the only way they could keep it stable. So yes, Kurt, and Kurt is following up on that question saying, well, why extract at all? It's water soluble. Yes, it is water soluble. And when I say extract, I am talking about a water extraction, not a solvent extraction. So those freeze thaws that I talked about, you're just doing that in water. You're not adding any acetone or methanol or any other solvents during that process. Tanya has asked a very important question about what the best standard is to calibrate the sensors. And this relates to Kurt's question. We at YSI recommend using rhodamine. Oh yes, thank you, Kurt. I just saw your comment there. Prozyme is the company that sells phycocyanin, and it is $400 for 1/3 of a mil. So when I bought it a few years ago, it was $1,200 a mil. So it sounds like it's still in the ballpark. But Tanya is asking, what's the best standard to calibrate the sensors? We recommend using rhodamine. And in the EXO manual, we describe a process for doing that. Now, rhodamine is what is called a secondary calibrator. The reason we use rhodamine, first of all, it's cheap. It's easier to get your hands on than chlorophyll or phycocyanin. And it is stable. So I was just talking about the stability issues with phycocyanin. Chlorophyll, you can get stable preparations of chlorophyll. The problem is they're typically in solvent. So it's very difficult to get a water-based preparation of chlorophyll that you can put an algae sensor into. Now that's changing. I think there are some new things coming onto the market that might be usable. The other thing, for those of you that kind of like to make life hard, you can actually do calibrations with cell cultures. You can calibrate with anything you want. We just recommend rhodamine because it's a lot easier to standardize and get a standard preparation of it than it is of the primary pigments themselves, or certainly of a cell culture. Still have good questions coming in here. So Carolina has asked a question that I do hear a lot, and this is an important one for us to take care of here because it clears up a lot of misperceptions. She is asking, what are the normal values of chlorophyll on a dam and the values that you see in an algal bloom? And I've been asked this question for years, and the unfortunate answer is there is no normal. This is why I was saying earlier, you need to use your sensor. The first year you use a sensor is the most valuable because that is the year you're going to start to understand what your background levels of chlorophyll are in your system. And then you're going to become trained to look for changes from that baseline. There is not a value of chlorophyll that means algae bloom, just like there is not a value of phycocyanin that means algae bloom. For example, I worked with someone in southeastern Ohio whose chlorophyll levels year-round bump along at 20 RFUs year-round. So he doesn't get excited until he starts seeing that value creep up to 40 or 50. I have other freshwater sources. Hillsborough, Ohio comes to mind. that are flat zero. They have, boy, if you're in Hillsboro, you're one of the lucky ones because you've got a great drinking water plant there that has a neat system and some of the cleanest water in the state. If he sees a chlorophyll value of 2 or 3, he's going to get excited. You know, so there isn't a magical number that you should care about. You have to establish what is going to matter for your monitoring program at your site. So Lisa has asked a question that reflects a hardened veteran of the EXO world, because she's clearly done a lot of calibrations, and she's asking, why do RFUs and parts per billion require separate calibration? Aren't the parts per billion determined using RFUs? The answer is yes, they are determined using RFUs. So it does seem like it would be an easy thing, but actually it has to do, part of it has to do with the temperature compensation of the channels. So if you are familiar with calibrating, you know that there's a temperature compensation you have to do. But it also has to do with that tuning process. Lisa, this is something, this actually gets into a very complicated answer. And so I'm going to, other than what I just told you, I'm going to set your question aside, and we may follow up with you to give you a little more background on that. Sorry, I'm looking through. We're kind of getting down to the last of the few questions. Some of these questions are things that we've already seen before. Here's a question about temperature. This is an important question as well. So the question is, given the strong effect of temperature on fluorescence, do the YSI probes take that into account? My guess is that they do not, but can this be done? So this is an important question, and actually, I think I have a slide that was a, oh no, I took it out of here. So for the other listeners, temperature and fluorescence are inversely proportional. And this will become apparent to you if you ever calibrate an EXO sensor, because the EXO sensor, you compensate during calibration for the temperature. Now, the problem is when you're measuring in water, you're not doing a temperature compensation. And there's a good reason for that. The reason is we do a temperature compensation when we're doing calibration because we know what the relationship is between rhodamine fluorescence and temperature. But in the environment, there can be a number of pigments and different types of algae with different concentrations of pigments that are leading to that fluorescent signal. So you can't really compensate on the fly, and I would advise against it, in fact, because you might introduce more error than you would actually remove. Now, there is one thing I do recommend, though, that if you're concerned about this, you might add to your practices. I strongly advise, if you know, for example, that your water generally ranges, you're going to be measuring water, for example, that generally ranges between 10 and 15 degrees Celsius, I would calibrate in that range. So you're going to compensation during the calibration process. If by contrast, you're going to be measuring water that's normally between 25 and 30 degrees Celsius, I would calibrate in that range, and you do a temperature compensation during that calibration. That is really your best defense in looking at temperature compensation and its effect on your measurements. But again, this is the type of thing that's going to have sub-RFU effects. If you are measuring down there in the 1 to 2 RFU range, this might have an impact on your data. For most people that are monitoring for algae blooms, this is not going to have a major impact on your data. So guys, it is after 2:30. I can tell you by the stack of notes here that Nate has handed me, we could go on for probably another hour, but unfortunately I can't go on quite that long. So we're going to go ahead and close today's webinar. I want to thank you guys very, very much. You've been a phenomenal audience, asking great, great questions. It's always a pleasure to do this, and we'll try to do it probably again next year. Everybody have a really great afternoon, and thank you once again for joining us.